Welcome to today's webinar and thank you for joining us. My name is Chris Huxley and I'm joined today by the author of TUFLOW, Bill Syme. He'll be talking to us about 1D, 2D linking, and in particular there's a couple of topics which he'll focus on. Bill will be discussing linking 1D channel network models with a 2D domain, carving 1D channels through 2D, connection of 1D culverts to 2D, and also underground pipe network modeling. Over to you, Bill, and thank you.
Hello to everyone. So I'm going to give a bit of an idea of some background and history to TUFLOW, and then I'll focus on a series of slides explaining how the 1D 2D links work. So for those who don't know, what is TUFLOW? The actual acronym stands for two-dimensional unsteady flow. It's a sort of name I came up with back when I was doing my research in 1989. And it solves the full 2D shallow water free surface flow equations. It came from a coastal background, so it has all the terms in there, including viscosity and wind and other forces on it. But TUFLOW actually also, the focus of my research was actually to link 1D and 2D schemes that hadn't really been done very successfully at that point in time. And the 1D solver that was available to me was named Estuary. It started off as a sort of estuarine modelling 1D system developed by BNTWBM in the 70s and then enhanced since then. But it solves a full 1D same knot equations, but since then it's been extended to probably have sort of the best pipe network manhole modelling system available these days. So you can really model everything from open channels through to your pipe open drainage systems. So TUFLOW is not just 2D, it's actually a 1D and 2D system. And probably the key to its success has been its 1D, 2D links. They've really been, they've worked very nicely. They're first probably out there in widespread use during the 1990s. And they've continued to be enhanced, and as a consequence, TUFLOW has been linked and integrated with Flood Modeler as well as two other systems. TUFLOW has been through the benchmarking process in the UK 2010, 2012 and performed well. And yeah, so it's a sort of proven, established system. It works very nicely, but unbiased of course. And its main areas of applications is in rivers and floodplains and in urban inundation modelling. But effectively, TUFLOW has two main types of links, what we call a HX link and a SX link. The HX is basically a water levels being supplied to TUFLOW by an external system, and an SX is a source of flows being supplied externally. And I'll explain those two types of links in the following slides. And these are ones that were developed and have been used for quite a long time now, and yeah, they work very nicely. So in its most simplest form, the very first link that was developed was the HX link, and the concept was, back when it was developed, that 2D models in 1989 were very, very small. Today they would run in seconds, but back then they would run all night. And it was just, the target was the estuarine coastal areas, and it was just impossible to have a 2D model that covered your entire estuary at a resolution that you wanted. So the objective of what we were about was to try and be able to have a 2D model in your area of interest, and then the rest of the tidal system you would model in 1D. And tidal modelling is quite important to model the whole system, otherwise you just don't get the right exchange of water coming through into your estuarine area. So what we set up and what we developed was the ability to basically transfer from 1D to 2D and back to 1D again. And it's, by today's linking standards, very simple, but it was what sort of started the process. Effectively what happens is the 1D comes in at the upstream end of the 2D area, and it's connected to what we call an HX link, and the water level in that 1D node is applied to the 2D cells along that HX link. the amount of flow that gets generated across those HX links. So if that 1D water level rises, that will push water into the 2D domain. If 1D water level drops, the flow will start to exit the 2D domain. So that flow, either entering or leaving the 2D domain, is passed through to the extractor from the 1D node. Now to set these links up, you basically digitize your HX line, and the key for the assumption is that the water level is the same along the HX line. So you really need to digitize that line. It can bend. It doesn't have to be straight. Along, a reasonably good estimate of what the water level contour would be. So it's generally typically digitized perpendicular to the flow. If you don't digitize it like that, you'll end up with some weird and wonderful flow patterns at that HX boundary. So effectively, these connection lines are provided, the CN lines, and the way to think about the CN lines is that they're transferring the water level from the 1D node to that point on the HX line. Now, because we've got two CN lines coming from the same 1D node, that means that all the 2D cells along that HX line will get the same 1D water level. So the water level will be the same at a particular time step along the HX line. Now what happens is an exchange of information between the 1D and the 2D every half time step. TUFLOW uses a two-step implicit ADI sweep solution, and basically it's an exchange of information at every half time step after each sweep. So when we're carving, the next thing we started to do was, in the mid-2000s, the idea came up, could we actually cut 1D through the 2D? So this is an interesting idea, rather than just have the 1D to 2D back to 1D, but could you actually carve 1D through the 2D? So we started testing this, and we actually found that by using the HX cells and applying the 1D water level profile along those HX cells, it actually worked quite nicely. So effectively what you do to set this up is your HX lines will normally be digitized along the top of the banks, or basically whatever the spill point is from your 1D onto your floodplain. You need to connect your HX lines to your 1D nodes using the CN lines, but rather than have this two CN lines from the one node going to the HX line, like in the previous slide, you have one CN line coming onto the HX line and then another CN line further downstream connecting in. So effectively what happens there in that little diagram is a water level of 10.2 and a water level of 10.0 at the next node downstream. So the cell at the bottom shown in red is about halfway, so it will be assigned a water level of 10.1. So each HX cell is assigned a water level linearly interpolated based on its relative distance from the connection lines. So it's very important that those connection lines are digitized pretty well perpendicular to the flow, because you're transferring that water level to the side of the riverbank. So if you don't, if that CN line went and was digitized further downstream or further upstream, you're effectively transferring the 1D water level incorrectly to the side of the riverbank. So those 1D water levels are linearly interpolated and assigned to the HX cells. Now as those HX cells become wet, they'll start to push water into the floodplain. And then as the cells become, the flow gets generated, that flow coming across the HX line is sucked out of the 1D nodes. Water can return, of course, back into the 1D system in a similar sort of manner. One of the important things to note is that the resolution of the 1D node is key. So you need to have enough 1D nodes that your 1D water level profile is reproducing reality. If nodes are too far apart, you'll be applying a rather bad series of water levels to your HX cells, and you'll get some really weird flow patterns. You also don't want to have your cross sections where nodes super close because you may only have 1 or 2 HX cells between each cross-section. So it's pretty nice to have at least 3 or 4 HX cells between your 1D nodes. Just on the HX linking, so another thing that's very important is to make sure you've got the spill height set correctly. So in that diagram on the left, the HX line is digitized on the top of the bank, but the centre of the cell is actually located down the bank a bit, and so the sample ZC value, the sample elevation, is actually lower than the crest. And so as the water level rises, if you didn't do anything to that elevation, then the water would spill across onto the floodplain too soon. As shown roughly where that blue height is. The next cell in will be the controlling one, but it's lower than the crest. So it's quite important to typically have a thick Z line, which is a thick break line, often the same alignment as your HX line. You can actually specify elevations along your HX line if you want to. There's a couple of options to do this. And make sure that HX cell gets raised to the crest height. So as the water level rises, it will spill at the right height. On the right-hand side of that diagram, there's another HX line. And because the riverbank continues to rise, in this case it's not so needed because the next cell in, away from the creek, away from the river, is actually higher, so it will actually control things. It's really only where you have a berm, a natural levee or man-made levee that you really need to have that thick break line to make sure your cells are at the right height. Another important aspect is your 1D cross-sections. If you're taking a 1D model that's been developed in the past, the 1D cross-sections may extend not just across the river but into the floodplain, so it's very important that you trim those cross-sections to the distance between the HX lines. So your 1D cross-section, to get the conveyance right of your system, you need to make sure that your 1D cross-section width at bank full is something similar to the width between your HX lines. So just another thing to check is that the exchange of flow between your 1D nodes is, you can visualize which cells are selected to do that. So in the diagram on the right there, this is showing the 1D 2D check layer that TUFLOW puts out, and that layer is either color-coded if you pick up the style highlighting in that GIS layer. If not, there are attributes that you can use to thematically map these color layers, these colored cells. And so, for example, those pink HX cells in the middle there, they will be associated with the node that goes from the 49.96 level to the 49.82 level. And so the flow that goes across those pink cells is what is taken in and out of that unit. Now, if you forgot to put in those connection lines, or that connection line wasn't snapped, you probably get an error message in that case. But if you forgot to put those connection lines in, those pink cells will continue on to the next node. And so as a quality control check, it's very important to make sure that your colors change every connection or every unit. Otherwise, you might be missing out on transferring one of your 1D water levels. Another nice thing about the HX link is that it's actually it actually applies momentum across its interface, its boundary. And that can be quite important in certain situations. And this image here is a nice example of some fairly wild flows. We have a creek, a 1D creek bending around there, and then you've got a 2D floodplain. Now this is into the height of the flood where the creek has basically in the top there is hardly flowing at all because the 2D flow is coming straight over the top of that 1D. So the HX link is very nice at sort of allowing that momentum of the water, if you like, to carry through. And you can see there's also a road crest or Z line in the red line. That's actually a road. That's an existing road where the water's pouring across. And there's a proposed new highway in the top right corner, which is what this study was investigating. And you can see down where that yellow arrow is, there's another short-cutting of a meander. You see the 2D flows are being generated very nicely across that HX link and back into the 1D system. So we do find that the HX link is very nice where you have these quite complex flows and you're trying to use a 1D representation for that embank, river or creek. Another nice thing about the HX link, if it is downstream control conditions, you're actually applying the full 2D shallow water equations. So that includes inertia, the eddy viscosity, and everything. If the flow is over a levee or a berm, it will actually apply the upstream control, and the weir isn't, and the berm isn't drowned out. It will actually apply the upstream control weir equation. So you're really covering all bases with this link, and it works very, very nicely. There's a nice little option. Sometimes if you feel there's some energy loss associated with water peeling off from the 1D onto the 2D, there's an option to apply an additional energy loss, which can be a nice calibration tool. It's not used that often, it's not necessarily that needed, but it can be quite useful. So I'll just talk a little bit now about the SX link. So SX link, as I mentioned before, is where TUFLOW is receiving a source of water, which is a flow. Now, in TUFLOW language, a source is a flow, but it's got no direction. So it's like rainfall is a good example of a source. A source can also be a sink, which is like infiltration or evaporation. So basically the water is leaving the 2D model in the vertical effectively. So there's no momentum associated with an SX link. The water is just either poured on top or sucked out. So effectively what is happening with the SX link is that the average water level along those, in the diagram on the right, we've got a single cell S link connecting a culvert in the bottom and two cells on each side of the top culvert, which is a bit larger. So the average water level, if there's more than one cell, is sent through to the 1D scheme, which then uses that water level or the drop in water level to work out a flow through the system. So this link is sort of ideal for culverts or cross drainage structures in a highway or an embankment, for example. As I'll explain, it's also ideal for modelling your pits and pipe system and pit entry points for your pipe networks. So the real trick, the SX is quite a nice, stable little link. It doesn't, as I said, transfer momentum in any way, so you have to be conscious of that. It's not normally a big issue in these cases, but if you've got a very large 1D structure, you may just want to check that whether that momentum transfer is needed or not. The only trick with the SX cells is that SX connections is that the width of the SX cells should be greater than the culvert width or the 1D element width, and I'm talking about wet SX cells. So if you, in that top example, if one of those SX cells was actually quite elevated and didn't get wet at all, well, that's not counted in that width arrangement. So you need to make sure that the elevations of those SX cells are probably below the invert of the culvert. At least one has to be below for the system to run. But it's quite important to make sure you've got enough width there. Otherwise, it's like you'll be pouring water into a thimble or something, and the model will probably go unstable. So the SX link, the other main use of the SX link is actually just to connect your entry points to your pipe network system. We call them pits or drains, a few terminologies, gully traps. And these are quite well suited to the SX link. So effectively you'll have 2D cells that are connected, and the pit has an elevation, like a spill level if you like. Now if that pit is not full, then the water just pours from the 2D system into the pit, and the pipe hydraulics calculations will proceed from there. If that pit surcharges and it's the same, that it's basically drowned out, well then the 2D water levels will be driving the 1D pipe hydraulic gradient. And the amount of flow going in or out of the pit is just simply applied as a single source to the 2D cell. pits are most commonly set up as depth discharge curves, depending on the type of pit. And yeah, this works very, very nicely.
Thank you, Bill. And as always, your guidance and advice is really much appreciated. Before we finish up, I'd like to introduce some of the support material that's available for people wishing to know more about 1D, 2D modelling. Let's start with the TUFLOW manual, which is available for download from the TUFLOW website. In the header there, you'll see the web link to the download page. We had a pretty major revision of the TUFLOW manual in 2016, and you'll now find that in section 8 there's an entire chapter dedicated to linking 1D and 2D models. So please look into that and have a good read if you're interested in knowing more. For those of you who prefer worked examples, you'll find the TUFLOW wiki a really useful resource. The wiki address is wiki.tuflow.com, and there you'll see, as highlighted in pink on this page, a list of all the different tutorial modules that are available. And there's 3 which will be of most interest to you. So module 2, 4 and 7. They each address 1D culvert linking, 1D channel carved through 2D, and also underground pipe network modelling. The datasets are downloaded from the website, and you access those via the tutorial model introduction link. And last but not least, we have the support team. If you have any questions or you're having issues debugging a model, please contact support@tuflow.com. This concludes our webinar for today. Thank you for listening. We look forward to catching up with you next time. Bye.